Okay, I begin by thanking the organizers for organizing this beautiful school and the conference where I learned a lot of interesting physics. There are lots of common interest. So I will be talking about our very recent experimental setup and some recent experiments. We are, what I would like to say, having baby steps in this domain of ultra-cold mass and spin imbalanced precision quantum measurements. So some of you have visited our lab over the past few days. So those who have not visited, so this is one part of the lab where we have the ultra high vacuum and where we simultaneously trap and cool sodium and potassium atoms, and we are also working towards making a two species Bose-Einstein condensate and Bose-Fermi mixture at the moment. So the programs we have in the laboratory are primarily mixtures of cold sodium and potassium atoms. I will try to motivate why this is. Then I will talk a little bit about the concept of spin noise spectroscopy and related magnetometry aspects using spin noise spectroscopy. I will not talk about something very interesting what we are studying at the moment, quantum diffusion and the impurity problem, which is one of the main motivation for the lab in the coming years. And then there are some very interesting results. Also, there was a poster by Gaurav, one of our PhD students, this trapped cold atom in structured optical potentials, and to look into many body physics. Also, we are interested in interactions between orbital angular momentum of light and cold atom. So these are broadly a few interests what we follow. So let me start by also thanking the group member, presently Anirban, Gaurav and Shairi, whom many of you know are in their second year of PhD in the lab. Sagar, who have started with me this experiment, just submitted his PhD and he moved just 2 days ago to start his postdoctoral work in University of Florence. And Dr. Maheshwar Shah, who defended his PhD last year from our group, who is a postdoc at Weizmann Institute. And we have Dr. Sanjukta Roy. She will be talking a later part of the day on her own experiment. She collaborates with us on the experiments. And we have a strong theory collaboration with Dr. Dibyendu Roy on the spin noise spectroscopy related studies, and Professor Supurna Sinha and Urvashi Satpathy, they are collaborating with the quantum diffusion. Okay, so these are some of the recent publications relevant to this talk. So this is where we technically describe our experimental setup, which was published last issue of AIP Advances, and also this made into the cover page of the journal. We are very happy. So I will talk a little bit about spin correlation spectroscopy from cold atoms, what we study, and this is a main article. We have also looked into the higher order spin coherences from thermal as well as cold atom earlier, and then we also use time resolved and vector magnetometry ideas using this coherence, spin coherence measurements. So I will talk a little bit about it, time permitting. So also I want to mention that this is 75th year of RRI, and this is one of our effort to create a hologram, which we also use to impart a holographic projection of light onto our cold atoms. I will show something later, and just wanted to pay a tribute to our founder. Okay, so what is the context and motivation which keeps us going? So there had been enormous progress with ultra cold atoms and Fermi gas and Bose-Einstein condensates in optical lattices. And for example, there was seminal work on superfluid Mott insulated transition, BEC-BCS crossover, then even in 2D materials, very interesting things. I also participated in some of the experiments during my postdoc days about the study of Bose glass to superfluid to Anderson localized ultra-cold gas systems. And then there were studies on the quantized vortices and BKT transitions. And many of these results, experimental verifications, were done using cold atoms. And this is actually one of the main strength of the field, which it demonstrated the quantum simulation effect. And most of these results were using single component quantum gas in optical lattices. On the other hand, there are very interesting recent results. For example, people were looking at mediated interactions between bosons and fermions. Jan Spillman and Subhadeep, they have done some interesting theoretical results. Recently, there was experimental demonstration of these mediated interactions between bosons and fermions. And then even recently, there are these correlated quantum gases, or what is known as quantum droplets, where the intra and interspecies interaction can be tuned to create exotic quantum phases called quantum droplets, and even more exotic quantum phases which shows up in dipolar quantum gas, which are known as supersolid phases. So very recent development, and a lot of exotic quantum states are being studied as we talk. So why we have chosen sodium and potassium? Because this is one of the very few non-reactive, stable, and possessing high dipole moment. So we can study dipolar quantum gas once we transfer them to the absolute ground state. And then also there are issues related to lighter boson mediating fermionic pairing and those kind of interesting physics which have important implication in condensed matter aspects. So those motivates us. So this is kind of initial days of design of our experimental setup. So where we had actually two sources of ultra cold potassium and sodium atoms, which are known as 2D plus magneto-optical trap. With a moving molasses, this intense source of cold atoms are pushed towards a central ultra high vacuum chamber where we capture large number of sodium and potassium atoms. At the moment, we are transporting this magneto-optically trapped atoms and transferred into the magnetic trap by a magnetic conveyor belt into what is known as the science cell, where we are planning to do the next phase of experiments. So that is the general idea. So this design of the ultra cold atom sources, that is something what we were even developing during my PhD days, and then later on applied to many atoms. And this has now become quite a standardized way of creating billions of atoms in a magneto-optical trap as a source. And this, this is kind of a bird's eye view of our experiment. A few months back when the table was less populated, so you can see the sodium laser system and the potassium laser system and all the acousto and electro-optic modulators to stabilize the laser systems are in one table. Then using polarization maintaining single mode optical fibers, we transferred the light into our main experimental system where the 4-chamber vacuum assembly is kept. And then we work at an ultra high vacuum range. We cannot actually measure the vacuum. It's below 10 to the power minus 11 millibar. We also have tested using our lifetime measurements of the cold atoms. And this gives a very long lifetime of the order of around 80 seconds in our trap. And then the lasers are stabilized. This is a standard technique. At the moment, we are also trying to improve on the resolution of our imaging system. We recently got the high resolution objectives, and then we want to eventually use it as a single site resolved imaging system as well. So this was sometimes back. For example, here is another eye view of where I also demonstrate. Maybe here you can see our digital mirror device using which we are creating this structured traps or structured potentials as well. Okay, fine. So this is what we were very happy about, very fast loading of the cold atoms. This is sodium, you can see by naked eye, it's quite bright actually in the lab, and even potassium. These pictures are taken by normal mobile phone camera because the fluorescence is quite large. Even though potassium is slightly outside our visible range, you can see a nice big cloud of the order of nearly a centimeter size. And then we can also measure how the atom number increases in the trap. And then, for example, we also see that we don't allow these atoms to stick to the glass surfaces inside our vacuum chamber. So we use what is called light-induced atomic desorption, and this also helps in increasing the atom number and the loading rate in the trap. So separately we study them. I don't want to go into too much detail. I just wanted to show that since our focus is to have a very large number of atom mixture in our trap, so we have spent considerable time characterizing all these parameters for the flux and the atom number in the trap measurements. For example, the magnetic field gradient, then the intensity of the cooling beam, detuning, and we do many studies. For example, Kanhaiya gave a very nice introduction about this various cooling processes, and then many things are also studied during this characterization parts and so on. Anyway, so how do we detect? At the moment, it's traditional absorption imaging. We shine a near resonant or resonant light. We look at a shadow, we image the shadow, and from the shadow, we extract all this information, how many atoms are there, what is their temperature, etc. For example, this is one typical temperature measurements for the sodium atoms, and we measure of the order of 160 microkelvin, which is good enough because we are also pushing a little bit with subdoppler to increase the transfer into the magnetic trap, and because we have a pretty deep magnetic trap, so things are getting transferred reasonably well. So then one of the things what we worry about is, I don't know whether you can clearly see, because this imaging light is a locked laser, very narrow line width, so it goes through various surfaces, and then there are interference patterns which typically limits the signal to noise ratio of our imaging system. So one of the study what we were doing, how to improve this signal to noise ratio in the images. So we take a path of what is known as principal component analysis based technique, which is pretty popular in the machine learning architecture, where facial recognition and other things people do. I was looking at some of the, so we apply those ideas, and what we actually do is that we take large number of reference and absorption plane frames, and then after looking at the interference pattern, we identify what are the principal component in space, and then we subtract them, and eventually we get at a very nice signal to noise ratio. So we are very happy with this technique. So we are trying to say that whether this will be useful for other people working in the cold atom domain and so on. So another thing what we were looking at recently is looking at the interspecies light assisted interaction between sodium and potassium, just by looking at the trap loss mechanism. And by taking this kind of very simple data, we eventually could extract information about, for example, when the photons carry or interact between the cold sodium and potassium atoms, how the presence of, let's say, potassium atoms causes the survival probability of sodium atoms in the trap. And then we do see a nice systematic effect. We can model it actually. And then also we can look at the off-resonant dipolar interaction just by changing the excited state population of potassium atoms and looking at the sodium survival probability. So these are some of the early indicators how these interactions are happening even at a reasonably thermal temperatures and so on. So I just wanted to highlight some of the other efforts what we do. For example, we have this digital mirror device. This is a 800 by 1010 micron size mirror, which we can also flip the full frame within a time scale of 100 microsecond. And then this can create a hologram of the trapping potential onto the cold atoms. And for example, this image quality is not that great, but on sodium atoms, we can actually create some kind of pattern. And this is one of the beginning days. It's more like a little bit fun images at the moment. So the outlook is that we can trap the atoms array for some quantum scalable systems. And then we have also this idea of creating random potentials, not just structured arrays. And then, many interesting aspects which we will not get into too much to do that. But one of the most interesting things we are recently getting very excited about is that we can also create what is known as orbital angular momentum of light by interfering through this DMD chip. And then we can actually create this helical light beam which carries the orbital angular momentum. And this orbital angular momentum we have tested by interferometric process. Here you can see this light with topological charge 1, topological charge 2, because you can just count the interference fringes at the left and right, and you can see that there are phase slips. And so now the next goal in the laboratory is to start interacting with this orbital angular momentum of light with the cold atoms, and also eventually with the BEC to transfer orbital angular. Okay, so I think I have some time left. So I will talk about this spin fluctuation measurements, which we started developing in order to develop it as a alternative non-invasive detection technique for the cold atoms. And then also along the way, we learned that there are possibilities of applications in magnetometry using this. So what is this spin fluctuation magnetometry or spin fluctuation measurements? So for example, the basic idea is that the atoms can be considered as tiny magnets. And once you realize that the atoms can be considered as tiny magnets, then for example, in rubidium atoms, you can also put an external magnetic field, and then those tiny magnetic levels will split. This has been discussed a lot. And then we look at the fluctuation of population between these Zeeman hyperfine or Zeeman sublevels. And then these fluctuations can be due to many reasons. It can be thermal bath coupling, quantum fluctuations, spin exchange collisions, everything. So we will not get into the cause of the fluctuations, but what it does is that in any of the magnetic sublevel, and if you place such an atom, a tiny magnet, in an external magnetic field, so there will be precision, and those precision frequencies will be at Larmor precision frequency. These are very well known now after so many nice lectures in the school. And now, so another idea what we use is that we look into the Faraday rotation. So, but in our experiment, we actually look into what is known as Faraday rotation fluctuation. So not a direct Faraday rotation. So this is what is practically happening if you have a linear polarized light, and then because it passes through the medium, it can be cold atom, it can be thermal atom, and because of the two components, right and left circular polarized light having different detuning, you will have a differential phase shift, and the light which comes out will have a rotated polarization vector. And if the populations are fluctuating or even density is fluctuating, then in that case, what you will have is that this polarization rotation will also start to fluctuate. It's a very, very small effect, but it is detectable. So now if there is this Faraday rotation itself, so here what we have done, we just let a bunch of cold atom pass through a probe, such a probe, and then in the red, we were just looking at the absorption near resonant. In the black, we were looking such a Faraday rotation itself from the cold atom. So this is, these people have done many, many times over the past 10 years or even more. Now, on the other hand, we realize that you don't have to measure a quantity directly. You can measure a noise associated to this quantity. This is also coming from a very old concept of Johnson-Nyquist noise. If you want to measure a resistance, you don't have to do ohmic measurement. You can also look at the fluctuation of the voltage across the resistance, and this gives a very good measure of the resistance itself through the fluctuation dissipation theorem. So we can use this for the polarization rotation measurement, and then this becomes now the spin noise measurement. So what is happening, imagine you have two magnetic substrate and the population is fluctuating, and that also means that the so-called the spin projection measurement over time, this is fluctuating, you will get a zero average, but the fluctuation is non-zero. So if you take such a measurement, Sx of t, Sx of 0, and that will be now proportional to the cos of Larmor frequency and something called an exponentially decaying term, which is inversely proportional to something called T2, which is known as transverse spin relaxation time in condensed matter system. So now using that, you can expect a signal appearing at the Larmor precision frequency with a width which is inverse to the T2. So this kind of things are reasonably well known in condensed matter system, where such a transverse spin relaxation time is very short and you get a broad noise peak. On the other hand, in atomic system, we have an advantage that the transverse spin relaxation time can be very small. Even in case of vapor with some buffer gas, you can look at the transverse spin relaxation time can be of the order.
This arises, you would be worried about T1, not T2.
Yes, I will come to that, because we also apply magnetic field, which is transverse, so in the void geometry. So, and finally, when you take this measurement, so practically the width is mostly given by that T2. T1 contribution.
No, but actually, I asked this because I have a different picture for the noise from what yours is actually. Should I say what it is?
Yeah.
So let's forget the field. And you have unpolarized ensemble. Then if you choose some direction, you will have a square root of n excess of polarization there.
Yes.
Now, if you have magnetic field, this will rotate. So if you detect the signal, you will see the noise signal, but you don't need actually any fluctuations of polarization. So in the rotating frame, for example, there's no so you don't need those fluctuations. It seems to me only once to prepare it.
Yeah, if you prepare the sample, yes, I agree with you. But then you can actually see the signal peaks at 0, and then there is a decay with the. So what I mean is that this will appear at 0 frequency, and then you will still see.
If you don't have a magnetic field, 0 frequency, but if you have a magnetic field, everything rotates. So then it will shift to the Larmor frequency.
It will shift to the Larmor frequency. But I do agree. So when I say that you are looking at a width, and if I claim this is totally T2, that will not be correct. There will also be a contribution from the T1. So I will come to that, hopefully, that when we do this. And then eventually, for example, even before getting to answer your question, I will come to this. So we were using this, for example, look at the so-called Faraday rotation fluctuation noise peak position, and for rubidium we were making a measurement with magnetic field, and as you expect that this kind of signals are seen for 87 and 85 both, and then we can even start to look at what is known as the differential spin fluctuation, and then this is happening because this separation is not exactly same as this separation. At high field, they start to separate out. We can nicely see that. And then more interestingly, you can even see, for example, the 1, 1 to 1, 0 and 2, 1 to 2, 0. They also shift because of the small GI value. And in all these things, you can actually measure in the noise spectra. So these are all in the noise spectra. And for example, you can even do a heat map of the signal, how it separates out as a function of magnetic field, and the fit is fantastic to give you a very nice, scaling with the Bright-Rabi formula. So these are nice things, and without even looking at the width. Now, on top of that, for example, since we can model this as you are mentioning that if there is a longitudinal component and also a perpendicular component of the magnetic field, the noise signal itself shifts, and this can be modeled very well. Means not just the peak position, but also the peak width, because it takes into account both T1 and T2. So this is modeled. Actually, we have done that in this reference. And in that case, you can also claim that this also is a direction sensor. So what we call that, let's say, vector magnetometer. And nice thing about it, it's kind of not limited to just a CRF regime. It can be extended to high field as well. And also we can see the time resolved Faraday peak position movement if I change a magnetic field, and this we can do of the order of millisecond time scale. And many of the biological processes, for example, happens in these processes, and this meter can be kept very far away from the body, and one can actually see when a heart rate creating magnetic field outside of the body. So now, so what happens is that we started looking into these spin coherence or spin noise in presence of optical pumping. If you optically pump, then you can actually start to see that some of the signals coming from the f equal to 1 will disappear if everybody is put into the f equal to 2, and which is expected. But once we started doing this, we were very happy to see that it can actually very nicely measure the relative population without even changing the population, because the optical pumping was done in a non-invasive way. So by doing this, we can actually see that how much of the degree of optical pumping one can measure, and which is an useful information. Actually, many of the application where you may want to know what is the relative polarization of your atoms. So these measurements were performed, and then another application what we wanted to have is that coherently driving the spin state. So if we coherently drive the spin state very close to the idea of CPT, coherent population trapping, and then one can try to see that if you have kind of amplified the so-called noise signal, and so that was the motivation. And indeed, we could actually see nearly 10 to the power 5, or nowadays we can even see a million-fold enhancement of the spin noise signal manifold if we do this correct, the two-photon Raman transition between the spin states. And the associated theory was also developed, and the reference contains a lot of information related to some of the questions. What is the definition of pi, sigma plus, sigma minus in this kind of configuration? And those are really detailed discussions, but in a nutshell, what we were able to show is that so-called spin noise signal, which is a fantastic technique, but why this is not so popular is because the signal strengths are usually very, very small. And here you can say 10 to the power minus 12 volts square per hertz. You really need specialized electronics to do that. We had to spend a lot of time to develop those. But on the other hand, nowadays, we can practically almost see this, what we call Raman enhanced spin noise spectroscopy, even on a spectrum analyzer directly. So this was great. And coupled with this additional enhancement, we started looking at this spin noise from the cold atoms directly. So, this is a proof of the principal experiment. We did additional probe and a pair of Raman beams, a pair of Raman beams through our cold atom sample. So this one is the probe, and we do the polarimetric balance detection and all the electronics, and then finally to see the spin noise signal, but it was enhanced by the so-called two-photon Raman transitions. And because of that, we were able to then start to see the spin noise directly from the cold atoms, and which was very nice because, when we tried to see first time spin noise from the cold atom, we were unable to see. Of course, we can measure if I spin polarize it, but a fluctuation in the cold atom is something interesting. I'll tell you why. Because I am also thinking that eventually I want to use this spin noise as a detection technique to know whether we have excess spin fluctuations or reduced spin fluctuation depending on quantum phase the cold atoms are put into. So some ideas on that. So, but the signals were not possible without the Raman drive. But with Raman drive, we can do that. Here we can actually show what are the optimum conditions for the Raman beam relative phase. And this also we did a kind of detailed study to finally find what is the best condition. For example, we were making this measurement in situ in a magneto-optical trap. Ideally, we should do this kind of experiment, transferring the atoms to an optical trap. But since in the beginning days, we wanted to do in situ, we also had to model the local magnetic field variation in the magneto-optical trap, but it works out pretty nicely, and we can actually demonstrate the Raman-driven spin spectroscopy from the cold atom. So what we are doing now, one of the recent results which are making us very happy is that this kind of 2-photon processes are not really 2-photon. You can actually even look at 4-photon and 6-photon and so on. And indeed, this gives us the first order and second order and higher order spin correlations. And so we are looking into this in detail. We are also trying to develop a theory with our collaborators so that we understand this processes clearly. And then together with that, now we are looking into, so this is something we recorded recently from the potassium spin noise signal, and we are trying to look what happens when we introduce sodium and when the interspecies spin-spin correlation, what does it do to the coherence, and if there is also a spin-spin collision shift, etc., because we can fairly well locate the spin coherence peak and so on. So, so these are some of the initial stages. So what I think I could do is that new machine where we want to study the ultra-cold atomic gas mixture. So I have given some of our ideas, what we want to do. Then the spin dynamics is a very interesting subject at ultra-cold temperatures, and eventually want to extend this to the BEC and Fermi gas, where very, very off-resonant spin probes can perhaps act as a non-destructive or at least non-perturbative imaging technique. And then this is one direction which we are very interested to go. This cold atoms in structured potential, and then looking at many body physics in arbitrary geometry and dimension. So also, it will be nice if someone is interested for postdoctoral positions, so can write to me directly.
Okay, questions.
The signal to noise measurement you showed in the last, the last figure, the last but one. No, later at the very end. Can you interpret this, where the structures come from?
Sorry? Okay, so this is very recent. This is something our PhD student gave me yesterday night. And after really taking measurements, making sure that, this is really coming from the atoms, she switches on the trap, switches off, Raman beam, all configurations and so on. So you are right. I'm also very interested to see, first of all, this asymmetry, because this asymmetry tells me something about also perhaps this is something to do with the local magnetic field issues, but the structures, I have no idea at the moment. So I'll be very happy if this is giving something more.
So what is meant by quantum fluctuations?
Okay, so one thing I can mention that this spins at ultra cold temperature. So we are at a temperature of the order of few tens of microkelvin. So the KBT is rather low compared to the lifting of the degeneracy what we can do. So you would normally say that thermal fluctuations, which might be the root cause of spin fluctuating from one state to another state at room temperature and so on, should not play a very important role. So there should not be any spin fluctuation. So that was something a year ago or so, even internally we were thinking that we are not expecting to see any measurement there. But then there is also other processes like spin exchange collisions and so on that can cause the spin fluctuating from one state to another, but they are not quantum fluctuation. But you do expect to see even leaving a spin at a lattice site, means out of nothing, it can flip its spin state from one MF state to another MF state. And people have studied in Mott insulator and Bose-Einstein condensate and those kind of effect. So what I wanted to summarize by saying quantum fluctuations are those effects which are actually making spontaneous spin fluctuations and so on. But there are experts who can mention more about what is the root cause of spin fluctuation at such an ultra low temperature.
Any other question?
Yeah. So in this very nice talk, firstly. So in this spin noise magnetometry, how should I think of sensitivity? Like if I think of it as signal to noise, there's signal is fluctuation.
Mm-hmm.
So what would be the noise? Like, is it a higher order fluctuation? And just connected to that, when you're actually adding Raman gain, does your sensitivity decrease? Do you add that higher correlation noise gets more noisy?
So
Like,
I would say it's the other way, because we actually can see, for example, the corresponding spin. So Raman enhanced spin noise, the corresponding signal to noise, at least in the absolute sense, the signal height divided by the short noise background. So that has increased. Now,
okay. So your noise is the photon short noise here. You do not see spin correlation
the background noise is the photon short noise.
So you don't see any spin correlation noise. Yeah?
It's a good question. Now the question is that at the stage, because I did not mention few other points also. This I skipped through quickly. I'll show you. See, for example, if you look at the integrated spin noise, so that includes not just the photon short noise background, and also with detuning, there is this atom number or the density effect. So a noise should be square root of the density, and then the area of the probe, and that comes in the picture, because if you have a very large probe, and these kind of things were also studied, then you do have the spin correlation kind of washing out. And we have actually done all these systematic studies by even looking at a smaller and smaller region to say that, because the ideal picture in the mind is a single atom spin fluctuation noise. Now, if you have many atoms, there is a spin correlation noise, if you mean that by your question, then indeed that is a culprit. So this should also be taken into account. And by the way, in the context of spin noise spectroscopy in solid state system, like in gallium arsenide and in quantum dots, people have studied, but there the spin correlation noise effects and so on are always ignored, because anyway the transverse spin relaxation rate is so small that those things are not seen. But yeah, this is a
has dominated your, when you have Raman gain, the short noise, like the optical noise should have gone up, no?
No, but the Raman, we make sure that the Raman
your noise floor should go up, no?
No, it doesn't, because we
But
don't
your short
detect that.
noise
We don't detect the Raman beams at all. See, we make sure that we are always detecting only the probe. And this is done very, very carefully, actually. If you see, means we make a small angle between the Raman beams and take the probe out. We really make sure that this is a point, actually, when we do not specially filter the probe and the Raman beams, all the problem happens. And this is a very serious problem, because if you look at our, I have not shown you, our short noise background is actually, we work at something like minus 100 means dBm level, and means which is where the electronics also starts to play a very serious. Yeah, we do that. Yeah, so for example, 1 year we spent just to get this thing come out of the short noise background. So these are of course short noise abstracted.
Just one
let-
more question.
Yeah.
So, sorry. So do you also consider spin diffusion effects? How big is your detection spot size?
Yeah. So as of now, our detection spot size is 30 micrometer, 30. We are also trying to reduce it of the order of a few micrometer. And this is actually something what we really want to study, the spin diffusion and also the density correlation extracted out of it. Very nice question. Yeah, this is something in the pipeline.
Okay, so let's thank Saptarishi once more.